To motivate what comes next, I'm going to have Mathematica do a few calculations. So we just integrated 1 over 1 plus x squared. Can you integrate 1 over 1 plus x cubed? Sure. And I hope it's not even too surprising that the answer involves arctangents and logarithms. Why? Because that's a rational function. Probably we would want to factor the bottom if possible and use partial fractions. And when we've used partial fractions, logarithms have become involved in the case of an irreducible quadratic, arctangents became involved. That shouldn't be too surprising. Does the corresponding improper integral from 0 to infinity converge? Turns out it does. And it turns out it still involves pi. How about that? What if we up the degree again to x to the 4th? Does that one converge? Yep, and it still involves pi. Fun, fun, fun. What if we upped it to 5? Does that one converge? Yep, and it doesn't involve pi, seemingly. Yeah, it involves gamma. What is that? That is the gamma function. What is the gamma function? Well, it's just a function you haven't heard of before. Or did I mention it in another class? I forgot. Okay. Okay. It's actually a very famous function. You just haven't heard of it before. Comes up in lots of applications. I can think of lots of applications in probability and statistics, for example. And it comes up in various spots in physics, for example. The gamma function. It's also related to the factorial function. Gamma of, for example, 5 turns out to be 4 factorial, 4 with an exclamation point, 24, 4 times 3 times 2 times 1. Gamma of 6, not grandma, gamma of 6 turns out to be 5 factorial, 120. Gamma of 7 turns out to be 6 factorial, 720. If you've ever dealt with the factorial function before, that's what we're talking about. If you haven't, don't worry about it. But you can't take like 1/2 factorial, can you? What's gamma of 1/2? It involves pi. Gamma, not grandma, gamma of 3/2 involves pi. But what is gamma anyway? I haven't told you. Okay, just other than to say it's a useful function. So this one doesn't seem to involve pi, it involves gamma. Can I approximate it? Yeah, I could do this. A little bit bigger than 1. Mathematica is predicting it converges to something a little bit bigger than 1. But how do we know it converges? In fact, can we even prove it converges? The answer is yes, and we're about to do so. Using something called the comparison test. Is it worthwhile to prove it? I claim yes. First of all, proofs help you think how to explain things clearly. And that applies more broadly than math. It applies to life in a lot of situations. It applies on the job when you want to ask your boss for a raise and you're trying to give justifications for why you deserve a raise, or maybe why you want your boss to buy you some software. Okay. It involves helping you in debating, whether it's political debates or debates about your faith with somebody who doesn't believe. It's useful for lots of areas of life. And yes, it does come up in math and justifying things and giving reasons for why things work. It's good to get practice with this comparison test now, here at the end of chapter 7, because when we get to chapter 9 on sequences and series, infinite sums, we're going to use a comparison test there as well as some other tests. And we'll be giving arguments, proofs there as well. So it's good to get some practice. What does the comparisons test say? Well, to tell you the truth, this step one that you see is not really part of the comparison test of the true test. It's just describing what to do. It's not really part of the proof that you would use when using the comparison test. The comparison test, the key parts are the first part here, the first sentence, in fact, assume f of x is positive. You need to be working with a function that does not go negative. You're interested in knowing whether this integral converges or not. The second key is these 2 bullet points. And we're going to use the first one. You've got some other function, g. That's what part 1 is about. Guessing what g should be. But for the official test, you've got some other function, g, where the graph of f is always below the graph of g. F of x, the outputs, are always less than or equal to g of x, which means the graph of f is always below the graph of g. And it says if you know the integral of g converges, the conclusion you can reach is the integral of f converges as well. On the other hand, if the inequalities between g and f are switched around, if the graph of f is above the graph of g, and you also know the integral of g diverges, the second bullet would imply that the integral of f diverges as well. We are about to try to apply the first bullet point to the situation at hand, integrating 1 over 1 plus x to the 5th. Although to make it a little simpler, the proof, we're going to actually integrate it from 1 to infinity instead of 0 to infinity. If the integral from 1 to infinity converges, so will the integral from 0 to infinity for this example. Although, as far as an exact value, it's even weirder, perhaps, well, maybe not as weird. Arc coth. I guess that'd be hyperbolic arc cotangent is involved, as well as pi, as well as the natural log function. Actually, if we're going to, well, okay. Yeah. There's the integral from 1 to infinity. It's pretty small, but it does exist, it seems. Proving improper integrals converge, when they do converge, is really also something necessary to do, especially in complicated situations, in order to justify that you can even numerically approximate. Because you could actually try to numerically approximate an improper integral that diverges, but that's kind of a nonsense thing to do. I mean, you could get an answer, but it would be way off, because the true answer would be quote unquote infinity. And here you're approximating it as some finite number. So you really do need to know integrals, improper integrals converge before you try to approximate. Okay, all that is preamble. How do we actually do the proof? So the goal here is to prove the improper integral of 1 over 1 plus x to the 5th. And again, I'm going to pick 1 to infinity instead of 0 to infinity. It's not that I couldn't do 0 to infinity. I could. It's just going to be a little bit less cumbersome to do 1 to infinity. We want to prove this converges. The guessing part that the book talks about, I'm going to label as intuition. The intuition stuff I'm about to write is not part of the proof. You do not need to show your intuition on the homework unless the book tells you to. I think sometimes they do tell you, they tell you to make a guess about what the function's behavior is like. So sometimes the directions do tell you to do this, but not necessarily all the time. 1 over 1 plus x to the 5th acts like, and I'm going to put acts like in quotes because that's kind of a vague phrase. Acts like, what does it act like? It acts like 1 over x to the 5th when x is large. That's a very vague statement. What in the world does it mean? And why is it relevant? I don't want to say they're approximately equal, because that could be misleading. The reason that could be misleading is because there could be other things approximately equal to 1 over x to the 5th, where the rigorous proof doesn't work, and in fact leads you to the wrong conclusion if you tried it. So I don't want to say approximately equal to here. I want to say it acts like or behaves like. I think the book uses the word behaves. Why does it act like or behave like that? Well, effectively, it's because we're focused on the highest powers of x in each case. The 1, the plus 1 in the denominator, in a sense, doesn't matter. You know, when x is 1,000, excuse me, let's make it 100 even. When x is 100, 100 to the 5th power would be 10 to the 10th. That's 10 billion. Whether you would add a 1 to 10 billion or not doesn't really affect the value of this so much. The graphs of these things get really, really close together when, and really rapidly, in fact, when x gets larger and larger. And so effectively, if this one goes to 0 fast enough to make its integral converge, then this one will go to 0 fast enough to make its integral converge. More precisely, though, to do the proof, we don't want to use approximately equal to symbols because those are vague. We want to use inequalities. I should first confirm f is positive. That's pretty obvious, actually. Then I should confirm the graph of f is always below the graph of g and that the integral of g converges. Once I've done those things, this first bullet would say the integral of f converges, and I would be done. But those other things, this one, and this one should all be checked. In your proof, you do need to say those things. The theorem, the comparison test here says assume f is positive. Because in theorems, you have to make assumptions to reach conclusions. When you do theoretical math, you build up from what are called axioms, which are actually assumed truths. And for us, effectively, assumed truths include all of arithmetic, like 1 plus 1 equals 2. Though if you dig deeper, you can actually try to go to the logical foundations of 1 plus 1 equals 2. And there's this, if you look it up online, proof that 1 plus 1 equals 2, there's these two guys from about 100 years ago wrote an entire book where it took them 300 pages to prove 1 plus 1 equals 2. And like every page was just full of symbols. It was like all logic. Crazy. But they did it. I don't know if anybody read it, but they did it. Anyway, we want to start from some basic assumptions. And in writing theorems, you also need to state assumptions because you would assume those things to prove the theorem is true. But to use a theorem, to use the test, we don't assume f is positive. We got to verify that. It's easy in this case. Let f of x be the function I'm integrating, 1 over 1 plus x to the 5th, and g of x be the other function that it acts like 1 over x to the 5th. Pretty clearly, f of x is positive when x is positive, or in particular when x is greater than or equal to 1. Note that f of x is greater than or equal to 0 when x is greater than or equal to 1. In fact, I can even say strictly greater than 0 there. It's not a big deal. That's pretty clear, right? I got a positive number. I plug it into x to the 5th. It's still positive. I add 1 to it. It's still positive. I take 1 divided by a positive number. It's still positive. It's very clear, but it does need to be mentioned. Also, What's the next thing to do? In order to use this first bullet, the next thing to do is verify f of x is always less than or equal to g of x. The graph of f is always below the graph of g. Is that the case here? Yeah, think about it. F is a fraction 1 over a number bigger than the fraction for g. The numbers in the denominator for f are bigger than the ones in the denominator for g, and therefore the fraction 1 over it, this is bigger, is less than that. Right? Think about an example. 1/3 is less than 1/2 since I'm dividing by a bigger number. 3 is bigger than 2. When you divide by a bigger number, you get a smaller number. At least when these numbers are all positive. Should we give a reason for that? It's probably worth focusing on the bottoms of the fractions first. Also, since 1 plus x to the 5th is greater than or equal to x to the 5th for all x greater than or equal to 1. I'm picking 1 here because that's the lower limit of the integral. But that would be true even if x were negative or close to 0. But these are positive, so that I can say, we can say 1 over 1 plus x to the 5th, which is f of x, is less than or equal to 1 over x to the 5th, which is g, for all x greater than or equal to 1. I'm almost ready to apply the theorem. Comparison test. What's the one thing left I have to verify? You remember? Does the integral of 1 over x to the 5th converge or not? It is important to say the word integral. Does the integral converge or not? The integral of 1 over x to the 5th, does that converge? Yeah. Why? I'm going to write is known to converge. Well, do we really know that? We actually have not done that example. So do we really know it? I'm saying yes, we do. And that could be confirmed in one of two ways. You could either go ahead and calculate it as a limit and see that that limit exists, or, and it's the or that you're going to do, use the fact in the box at the bottom of the same page, page 419. The comparison test is at the top. This box is at the bottom. These are known facts, useful integrals for comparison that you may take to the bank to be true. And I'm even going to allow you to use more general facts that will give you more flexibility in your proofs. This one says the integral from 1 to infinity of 1 over x to the p converges if p is bigger than 1, like if p is 5, and diverges if p is less than or equal to 1. We did the calculation for this example on Monday with p equal to 2, and we saw it converged. And then we did p equal to 1/2, because we had 1 over square root of x, and we saw that that diverged. This integral, which we did just 30 minutes ago when p was 1/2, converges in the opposite case when p is less than 1/2, and diverges if p is greater than or equal to 1. So when p was 1/2, just 30 minutes ago or whatever it was, we saw that that one converged, although I had a 9 up there instead of a 1. And this integral is something we did after the gateway on Wednesday, except I used a k instead of an a. You may take these facts to the bank as being true, and you may use them whenever you need. You may also do the following. You might want to make a note about this even in your book. This lower limit of this integral being 1 could be changed to be any positive number, 2, 3, 4, 5.7, 0.23. Any positive number down there is okay to work, and the same fact works. Also, for the numerator, that can be any number, and it works. It can be any positive number, 2, 3, 4, 5, 6, etc., or 2.7 or whatever. Could be a negative number as well, and it still converges when p is greater than 1 and diverges when p is less than or equal to 1. You may use that more general fact. The number down there does need to be positive, but the number up there can be positive or negative. For this one, the 0 needs to stay as 0, but the 1 can be any positive number. And that one on top of the fraction can be any number at all. And the fact is still true, and you may use it. And finally, for this one, keep the infinity as is, but the 0 down there can be, in fact, any number, positive or negative, as long as it's a plus infinity up there. And this could have a coefficient in front of it, like a 2 or a 3 or a 4 or a -5 or a -7 or whatever. Any coefficient in front of it, and it's still going to work. But the a does need to be positive, and that does need to be an infinity. So you may use these more general facts anytime you need them while doing a comparison test proof, like on the assignment due on Monday. Say it again. The 1 there can be any positive number. The 1 up here can be any number at all. The 1 up there in the upper limit of that integral can be any positive number. The 1 there can be any number at all. The 0 there can be any number at all, positive or negative. The coefficient of e to the negative ax, which is currently 1, can be anything. But the a does need to be positive. And these conditions on the p need to be kept as is. So I'm going to use this here. For the example, we're doing p is 5. G of x is 1 over x to the 5th. So the p is 5. 5 is bigger than 1. We know this integral is known to converge. Page 419 if you want to reference. What do we do next? Are we done? No, we're actually not done. We need to state our conclusion. We have set things up so that we can apply the comparison test. We have verified f of x is positive. We have verified f of x is less than or equal to g of x. We have verified by a known fact that the integral of g of x converges. Therefore, by the comparison test, the integral we're interested in converges as well. 3 dots means therefore, 3 dots. Therefore, the integral that we're interested in, which is the same as the integral of the f of x, converges as well. Converges as well. When a mathematician finishes a proof, they get excited, they celebrate. QED means they start talking Latin. QED, quod erat demonstrandum, means I demonstrated what I wanted to demonstrate. So Christian mathematician, I put PTL for praise the Lord. Maybe you put a smiley face. Nicer smiley face. Sometimes you see boxes that are shaded, colored, or slashes, or maybe stars or something like that. Maybe lots of stars, you're so happy. You're done with the proof. Now you might look at this and say, did I really do anything? It seemed like I was just sort of stating stuff. And I'm answering, yes, you did. Or yes, we did. This is a logical argument allowing us to conclude by the comparison test that our integral converges, which you definitely would want to know for sure without a doubt before you would try to approximate it. And again, it does make sense. If you graph the two functions f and g, g of x equals 1 over x to the fifth versus f of x equals 1 over 1 plus x to the fifth. The graph of f is always below the graph of g. Since the integral of g converges, this purple shaded area is finite. It should make intuitive sense that the area under the graph of the red function is also finite, even though the regions go out forever and ever. The improper integrals converge. Picture's not a proof, though. We want a logical argument. Picture's nice, it's not a proof. Reason is pictures can be misleading. You can be deceived by pictures. As a simple example, you were trying to show the function x squared minus 2 has a root. Most people would say, hey, look, it crosses the axis, done. Problem with that is, how do you really know it crosses the axis? Because in making the drawing, you're assuming what you want to show. You're assuming that the graph is continuous, for one thing. No breaks in it. That's cheating. You can't assume what you're trying to prove. How do you really know for sure, without a shadow of a doubt, that it crosses the axis? How do you know it's continuous? You have to prove those things. Picture's not good enough. For one thing, pictures can be deceiving. For another thing, sometimes in the picture, you're really implicitly assuming what you want to show.